lecture, we talk about insertion sort, right? So now, okay, and we say like insertion sort is not a very good sorting algorithm because a syntactic analysis gives us like n squared complexity, right? So let's now consider a different sorting algorithm. We call it merge sort. Okay, which supposedly you should also learn that from data structure. Right? So in the merge sort, basically, okay, again, given a array, okay, unsorted array. So if n is 1, if you only have one number, obviously it's already sorted. One number is it must be sorted. Okay. If it's more than 1, you are going to recursively sort the first half and the second half. How do you do that? It is a recursion, so you don't need to worry about that. Assuming it has been done. Assuming it has been done. Okay? So now you have two different sorted lists. Okay, two different sorted lists. You need to merge them. You need to merge them into one sorted list. Okay, so only these 3 steps. So the first step is easy. Nothing needs to be done. Second one is you rely the second step on the recursive calls. So the second step is also easy. I mean, conceptually, it's easy, but in theory, in reality, you need to go into like a lot of recursive calls, to a very deep one. But that's the computer will deal with that. How about the third one? The third one is our key routine, the merge. How do we merge two sorted lists like effectively, efficiently? So here's the thing. Okay, you can see that we have these 2 sorted lists. Okay, these 2 sorted lists. The first one and the second one. Let's look at these 2 lists. What should I say? From bottom to the top. From bottom to the top. So this is the first list is 2, 7, 13, 20. The second one is 1, 9, 11, 12. But we only look at the first number of these 2 lists. Okay, which is 2 and 1. You only compare these 2 numbers. So when you compare these 2 numbers, obviously, 1 is the smallest, is a small number, and it is guaranteed to be the smallest number, in both lists, right? So you will move 1, to this place. It is already sorted. Okay? And then, the second list will, you will have 1 fewer number. Okay? So you have like the first list remains the same, but the second list, okay, the first number of the second list becomes 9. Again, you compare the first number of these 2 lists. So obviously 2 is smaller than 9. So you move 2 to here. Okay. Then, okay, you are going to end up with like 2 lists like that. Again, so you can see every time when you do one comparison of the first number of these 2 lists, you are able to, find a rightful place for one number. With 7, 9, okay, you are going to move the 7 here, and then the first list becomes like this. So keep doing that. Eventually, okay, you are going to end up with 1, 2, 7, 9, 11, because like you know, all these numbers add up to be n numbers, right? The first half, the first list is you know, n divided by 2 numbers. The second list is n divided by 2 numbers. So total number will be you know, n numbers. And every time you compare one comparison, you are able to remove one number from these two lists. So totally, okay, the number of comparison at this move will be bounded by n, right? Okay, so the time required to do the merge is theta n. Okay, to merge the total n elements. Okay, then the time complexity of the merge sort is actually, you know, let's look at this. Okay, if A is 1, it's done, so it's theta 1. It's basically just one up, just constant count. Okay, so and you are going to the second step. You recursively call, you know, recursive merge sort on first half and the second half. So it's 2 times t times n divided by 2. Okay, and the third one, as we already discussed earlier, is theta n. So Tn is going to be, you know, either this one or this one, depending on the size of n. Okay, either theta 1 if n is 1, or 2Tn divided by 2 plus theta n if n is greater than 1. Okay. There's a small sloppiness here because when we do recursive calls, actually, you know, because we divide this the whole array into 2 halves. One is like you know, n divided by 2, like upper bound. One is n divided by 2, lower bound. Should be something like that. But they are close to n divided by 2, so we just like you know, just write like 2 times t n divided by 2. Okay. You can prove that it does not affect the asymptotic analysis. But no, I will skip that. I will let you guys to think of why it does not affect the asymptotic analysis. Okay, try to think about that. Okay, but okay, because this intuitive speaking, each of them is close enough to t n divided by 2. Okay, but if you come from math department, you want formality, then you need to prove, okay, asymptotically, this equal to, this one. I should use equal. I should say this one and this one will result in the same asymptotic complexity. Okay, but anyway, okay. So in reality, it's what happens is that P of n equal to theta 1 or constant in phase 1, or 2 times t n divided by 2 plus theta n is greater than 1. Okay. So the base case, like when Tn is equal to theta 1, is when A is sufficiently small, it should affect the symptotic analysis. The CLI's lecture 2 provides several ways to find a good upper bound of T of n. We will talk about like how you can solve this in this lecture 2. But what is CLI's? CLI's, C stands for Coleman. Okay, Lester, L is Lester. R, S, actually the textbook is written by 4 authors. So they're like initials completely together with the CLI's. This stands for the textbook. Okay. So how do we solve this? Here, let me give you a very intuitive analysis. So Tn equal to this one, and let's assume that because it's a constant, this theta n, let's assume this is Cn, okay? Where C greater than 0 is a constant. Okay. This one is just represent this one. Okay. So we put T of n here, and then according to the recurrence relation, it will become this one, right? Okay, and each of them, according to the recurrence relation, becomes this one, right? Right? So you keep doing that. Eventually, it becomes theta 1, right? Okay, so how many times does it take to become theta 1? What is the depth of this tree? Because each time you get, you go down by one level, okay, you divide this number by 2, right? Okay, so you divide n by 2, you divide n by 2, so it becomes n, T of n becomes T of n divided by 2, T of n divided by 4, T of n divided by 8, and so on. So theta 1, the number of levels actually should be log 1, right? Okay, and if you look at each level, this level gives you Cn, right? The first level gives you Cn. The second level, Cn divided by 2, plus Cn divided by 2, it's a Cn as well, right? The third level, Cn divided by 4, you have 4 of them, add up to be Cn, right? And you will soon find out. Each level gives you a Cn. Okay? So what happens? Like you have this many levels, and each one will give you a Cn. So total, the leaf nodes, okay, you have n leaf nodes. Okay, n leaf nodes. This n leaf node gives you theta n. Okay, so except the leaf node, the leaf node gives you theta n. Okay, all the other give you Cn times log n, right? N log n has a higher order than theta n, right? So this one doesn't matter. So in the end, a symptotic analysis gives you theta n log n. Right? Is this the worst case or average case? By the way. Huh? For all the cases, yes. In merge sort, there's no worst case, there's no best case, there's no average case. Basically, every cases will go through similar process. Okay? So you have n log n. So obviously, the merge sort, in terms of a symptotic analysis, okay, it grows more slowly than theta n squared. But in reality, even though merge sort symptotically is a better algorithm than insertion sort in the worst case, but in practice, merge sort only beats insertion sort when n is greater than 30 also. Okay? Remember, I told you, like the lower order terms also matters when, in practice. So yeah, but when n is large, Yeah, merge sort is obviously better solid element. And you can test it out by yourself, and whether or not merge sort is indeed a better solid element. In fact, yes, our first program assignment, as I will show you later, okay, is related to solid elements. But it's not just for these two solid elements. We are going to talk about many different solid elements, and the first homework assignment, the first program assignment, involve all these solid elements. Okay? So, yeah. That's about it for the first lecture. And because it's the first week, so we will stop here. Okay? And I will give you some time to rest, and give myself some time to rest. Okay? And we will see each other again next week. Okay? Any question? So this is my teaching style, okay? I will talk about most of the material in English, most of them. And if some material are, I think it's probably difficult to understand, I will also explain again in Chinese. But if you feel that some places you don't understand fully, I mean, you can always raise your hand to stop me, and I'll be very happy to repeat or to try to explain in a different language. But if you don't, say anything, I will continue, to teach the following stuff. So, please, if you want me to, teach slower, you can give me a hint or something. I welcome you to give me some feedback. Okay. And again, I encourage you to come to lecture, but I do not take attendance. Okay. So that's it today. Okay. I'll see you next week. Okay. Bye.